So what I'm going to be doing today is formalizing a bit of point set topology in a proof assistant called coq. And if you don't know, point set topology is a branch of topology that deals with describing spaces as sets of points, because of course there are other ways to describe spaces. And coq is a proof assistant that is a program that will check correctness of your proofs. And in particular, this one is based on dependently typed lambda calculus and inductive constructions. So on the large scale, I'm gonna be following the structure of the book by Moncrief, Topology. Might as well try to do some of the exercises. So I've got here this library that depends on the built-in library of ensembles, which is a fancy word for subsets of some universal set. Like we fix some set that we consider universal, and then we talk about various subsets of that. And the standard library defines some operations on these sets, but unfortunately it doesn't define many theorems about them. And so in particular, defining theorems about ensembles depends on what your foundations are, whether you're doing classical or constructive reasoning. And there isn't really much point in doing topology constructively, or rather, it is much more difficult for very little reason, and I'm doing classical topology here. So I've defined a bunch of theorems regarding these sets using classical logic. So in particular, there are some theorems here that are not true constructively. I'm also using extensionality of propositions and functions, which means that I'm able to say that one proposition is equal to the other, where equal means I can substitute one for the other. Again, these are some additional assumptions that are not true in vanilla coq, but they are very mild assumptions. So I have defined this library here with a bunch of theorems that will come handy. So let's start by formalizing the concept of a topological space. Let's start with that. So a topological space on some set X, which I'm going to go with type, consists of, going to name some constructor. So it consists of some set of open points, open sets. So here, X is our total space. Ensemble of X is some subset of X, and then ensemble of X is some set of some subsets of X. And this collection of open sets has to satisfy some axioms, such as that intersection of two open sets is open. So if we have some U and V, and then U is open and V is open, then their intersection is open. And before we can continue with this, let's actually import our library. And I'm gonna need to do a few more additional things. I'm gonna declare the first argument of the intersection operation implicit. That argument is the universe in which we're working. It's always going to be evident from other parts of definition what the universe is. And so we can define a data type like this. This is basically a dependent sum, which is to say it's like a record that as the first component contains the set of open sets, and then other components are proofs about the set. Now, for the definition of a topology, we also need the full set to be open. The full set is when considered. Oh yeah, I also need to do the same thing with the full set. The full set, like if we're talking about subsets of some universe, then the full set is of course the entire universe. And we also need that an arbitrary union of open sets is an open set. And for that, we have a thing called family union, which from a function that takes some index as input and outputs a set, it takes the union of all the sets iterated over all the indices. So, well, not really a function, but a construction. So if we have some family, I should probably say that these are ensembles over X. So here we have a family that is indexed by some indexing set I. And we have an ensemble, and well, we need the I as well. It needs to be some kind of type. So suppose that each Fi is open. Then we would like to say that their union is open. That should compile. And just like that, we have a definition of a topology. I could probably add some formatting, like try to fit it roughly within the screen width. I would like also to adjust do this. I declared this parameter implicit so that the constructor and then the fields would automatically pick it up as implicit, but in the actual data type, like in the type, I would like to be explicit about what is the universe that we're taking like points from. This okay, what shall we do next? We can prove a theorem that a binary union of two open sets is open. Let's make this implicit. So if we have some topology T, then we have some some sets, and suppose that U is open in T, and then V is open into E, then we know that the union of U and V is open, and then I'm also going to need to declare the arguments of the union. What are we missing? Right, this should be a T. Let's get this on a new line. So the way we do this is we can imagine a binary union as a union of a family of two elements. And so we have a function for that, a theorem for that. I forget what it's called, but we can look that up. So we have this family here, this theorem here. And so what we can do is we can represent a binary union of two sets as a union of a family that is indexed by a boolean here, which in case of true it returns the first set, and in case of false it returns the second set. So what we can do is rewrite family, what was it called again? Family union binary. And so we have changed our goal from this to this. Now we can apply the theorem that a family union is open if all the elements of the union are open. Oh, it's not a rewrite, it's an apply. Now we have to prove that all elements of the family are open. So we have a boolean, and there are only two values that the boolean can take. So if we immediately pattern match on this boolean, we have two cases to consider here. Well, we know that that's a hypothesis that we took from here. So we can say assumption. And then this branch as well. Well, we could also say apply V. But actually, in like both of these cases are simple enough that you could just say something like this. Now is a tactic that does whatever is next, and then if the resulting sub-goals are simple enough, it just solves them. Are you aware that your audience has no idea how cock works, not even the basic syntax? Well, I'm assuming that part of my audience knows some of the things about cock, because this isn't really the first time I'm streaming cock, but the first time I'm on YouTube. I guess I could go into a little bit of detail into how cock works. So when we start a theorem, we have, well, whenever we are in the theorem, we have a set of assumptions or hypotheses which are available in the scope, and then we have one or more goals, which are the statements that we're trying to prove. And then we in sequence, we apply tactics to our proof. And tactics are things that manipulate these goals and assumptions. So for example, the intros tactic, which stands for introduction, it takes... so if the goal is an implication, it's going to take the left-hand side of the implication and introduce it as a hypothesis. And then whatever is left is going to be the new goal. And so here, for example, I'm introducing two statements as hypotheses from the goal. And I'm left with the conclusion of whatever was in the goal. And now, for example, rewrite. Rewrite is a tactic that takes an equality. So I have this equality here. this equality here, and it replaces the left-hand side with the right-hand side in the goal. So just like that. And then applies a tactic that applies an implicational lemma to the goal. So that's like the basics of it. Anyway, okay. Another theorem that would be able to prove is that the empty set is open. And again, I would need to make the arguments of the empty set implicit. Now, we are again going to use the family of sets, union of a family theorem, and the way to get the empty set from a union of a family is to take union of no sets, so an empty family. And again, in this library that I have here, there is a function that a theorem that shows that. I think it's called family union empty. Right. So family union of an empty family. The family is empty because the indexing set is false, which has no inhabitants. So the family union of this empty family is the empty set. And now we again apply family union open. And we would like to prove that all sets in the family are open sets, but there are no sets in the family. To show that, we have to pattern match on the index, which is an element of false, and there are no elements of false. So we kind of do like a case analysis where there are no cases to consider. Now, we can make this a little bit nicer if we added some notations for set operations like intersections, unions, and all that. And in this library in particular, I already have defined some notations. So one interesting thing about Coq is that you can define arbitrary notations, like extend the syntax in arbitrary ways at like random parse rules. So these are kind of things that I would like to have here as well, but with some slight modifications. So to begin with, I'm going to take these. I'm gonna take all of these, but I'm gonna modify them slightly. I will also need these. So I don't particularly care about \n. Okay, let's change these settings for arguments of all of these. What am I missing? Ooh. Full set, empty set, union. And complement. family union and family intersections are already configured the right way. Now that means that I don't have to include these underscores in the notations. Cool. So one thing I can do now is in this definition, instead of saying intersection with letters, I can use an intersection symbol. And also instead of saying family union with letters, I can say big cup I into a phi, which kind of mimics the notation that you get in mathematics. That's the idea behind it. Here again, cup. And I could also introduce a notation for the empty set, but there is no, well, like, consistently used notation for the full set, and the two are kind of dual, so I'm not 100% on how to, like, whether I want to do this. But the one thing that I wanted to change from this notation is the following. So I could define a record that is, so I could define the concept of an open set as a thing, because currently we have a predicate that's called open, which takes a set and then it's a statement that this set is open. But we could define an open set as a thing. So we could define a new data type that is parameterized by the topology and also necessarily by the set of the set over which we define the topology. It would consist of some set and also the proof that it's open. So here we are referring back to the field that we defined here. And so obviously, because we have this, because we have this theorem here, we could talk about the union of two open sets as things, because the union of two sets that are open is also open. But we would not be able to use this symbol here to denote it, and that is a thing that we would like to do. So one way to do it would be to define a slightly more complicated notation, which includes some tactics that try to solve for the right kind of result for us. And so the way we could do this is, say here, I'm gonna define a new tactic called downcast. And the reason it's called downcast is because it's kind of analogous to downcasting in object-oriented languages. It's going to take some term x, and then it's going to try to generate a term that is like x, but possibly with some additional structure. So the first thing it's going to try to output exactly x, and if that works, then that's okay, but it might be the wrong type. So for example, we could try request a union of two things and then request that it has the type of an open set. Then an exact is not going to work here. Otherwise, it's gonna try to instantiate some sigma type thing where the first field is going to be that open set, so like this. the tactic exists, we'll try to instantiate a record like this by supplying the first field, in the assumption that all the remaining fields are proofs that we are left to prove. So all these remaining proofs will need to be proved here. And for that, we're going to use eauto with downcast, where downcast here is the name of a database of hints, which we're going to define. We're going to populate it with some theorems, which would let us generate proofs for these remaining fields. And the nice thing about this is that we can populate this database at a later point, so it's kind of extensible. And just as a safety measure, I guess, if that process fails, so what eauto does is it tries to generate a term that fits the right type out of pieces that it has in scope, and out of pieces that are in some database of hints. Now, if that in case it fails, it doesn't like throw an error, it just doesn't do anything. So if there are any remaining goals to be solved, we would like to fail. So we have a tactic like this, and now we can say that union of A and B is actually LTAC of downcast of the union of A and B. Right. Only parsing. So because this contains LTAC, then the coq pretty printer will not be able to use it for outputting. What's coq? Is it an entire language or a distributor? So coq is an entire language. It's actually a mix of 3 languages. The first being like a flavor of lambda calculus, which we use as like the internal representation for our proofs and structures and data. So this is an example of what that thing looks like. Then it's a language of tactics, which we use to manipulate proofs in a high-level way. And then it's also like a language of declarations, which are all these big keywords highlighted in brown. And this program here is the default IDE for coq, which a big thing about coq is that it's an interactive theorem prover, so the only reasonable way to do proofs in coq is by interacting with the IDE. So if like you're looking at some sort of proof, you need to see these things to know what to write next. And that kind of sets it apart from other proof assistants, I think. At least there are other very popular proof assistants that are not like this, and this is a very big difference, I think, in the way you approach doing things. Anyway, so what we just did here, so in fact, without noticing, we redefined this theorem in terms of the new notation here, and the nice thing is it's backwards compatible with the previous notation. So what happened here is that we constructed the union of U and V and then passed it down to downcast, and this exact tactic was able to finish. So let's prove a theorem that the union of 2 open sets is open. I mean, that's the theorem that we have here, but we're gonna need a slightly different version. If we have U and V, which are two open sets as objects, then we would like to be able to prove that if we turn the first into its set of points and the second into its set of points, then it's gonna be an open set. The reference B, I'm sorry. What is B? Also, someone is pinging me. Okay, that's not important. Let's check. Is this coming from here? If I say it like that. Interesting. Oh, I think I know. It hit an unknown identifier and then it somehow got renamed into something completely useless. Anyway, there is also one nice thing we can do here. So here we are turning open sets as objects, this U, into sets. So we are upcasting. And this is a thing that we can actually always do, and we can achieve this with a coercion. So open points also is a projection from this record, and we can use it as a coercion from an open set as an object to just a set. Like that. And now we can write, instead of open points U, we can write U. And that is implicitly coerced to using this thing to a set. So in fact, even when printing, it says union of U and V, but union takes two sets, and then we have two opens here. So what's happening is that it's actually implicitly converting them, which you can view if you want to. So the proof to this should be really trivial. We just apply this. I guess we'll have to, yeah, so first we apply union open. Then we have to show that whatever U coerces to is in fact an open set, and the way to do that is to destruct the record that is U. So it's a record of some set and some proof, and now in fact, well, this looks very complicated, but we can simplify because this is a function, this is a projection applied, well, not a projection, the coercion is a projection applied to a record. We can simplify this, and now this is a thing that is directly available in among our hypotheses, so we can say assumption. But instead of that, I'm going to go for the shorter now destruct U. Similarly here, we can now destruct V. And just like that, we have a theorem. Now, let's hint resolve union open downcast. Downcast. So we're gonna add this theorem to our collection of theorems that we are allowed to use when downcasting. And so let's test this a bit. Suppose we have some set X, and then we have some topology on X, and then we have U and V, which are open sets in this topology. Yeah, X is a type. Now, don't do this in actual Coq files, but like this is just for debugging. We would like to check what is the union of U and V. So it's a subset of X, which is okay. The U gets coerced to a set, and the V gets coerced to a set, and then we take a set union of the two, and we get back a set. But what we would like to be able to do is to say that the union of these two is actually an open set, which reasonably it is, because we've just proved that. And this is a thing we can in fact do. This is what this notation has done for us. So we use this tactic here to elaborate the union of U and V into a record, an object of type OpenT, where the first field, the set, is what we told it. And then the proof that it is open is generated for us using one of the theorems that we defined. Well, so far the only theorem that we defined. And this is kind of a nice trick that that you can use to overload some notations like this. And in fact, I'm probably going to add a lot more overloading to this, and by which I mean currently we have a meaning for the union of two sets. We have a meaning for the union of two opens. There's probably also going to be closed sets, clopen sets, neighborhoods, and perhaps even more. So anyway, let's add the exact same idea to our intersections, to complements, to, can we add the same to family intersections? Yeah, we probably can, although writing down the right lemma for that to work out is probably gonna be not that simple. What am I missing? Right, I should say that it is only for parsing. Again, because Coq tries to reuse notations that you use like in your input, it tries to reuse them to also output when it pretty prints things for you. It cannot do that when like you are generating terms using tactics. What are we missing here? Variable I wasn't found in the current environment. That is interesting. I think I broke the big cup tactic notation. Okay, I'm gonna undo this for now. Right, so that is what's broke. What has been broken. This is probably because I is not typed. We're not assigning any type to I here. Right. Yeah, that is probably true. So user says that there are issues with what variables are in scope and use LTAC notations. Yeah, I'll have to investigate this in more detail off stream, but yeah, okay, I guess for now let's, oh no, that's the wrong undo. For now, let's get rid of these whack notations in family unions and intersections. Probably not gonna get to fancy enough things to require these yet, but in the future definitely. What am I missing? Right. Okay. Now empty set. Open. In fact, one interesting thing that we could do, we could define what is it called? Like a notation that is a synonym. We could just define it with notation for now. We could define actually the empty set keyword to be a notation for downcasting like the actual empty set. Only parsing. Move the period. And right, I'm assuming that's not recursive. If it is, we could use a qualified name for the empty set. So the reason why I'm doing this is that I want empty set to also be polymorphic in whether it's a set, an open set, or whatever. And similarly for the full set. So yeah, so now we have record open. Right, so now we could define some similar theorems for intersections to begin with. What went wrong? Full set. Oh, that is not good. Right, so it's choking because full set has an implicit parameter. That is, if I say something like this, that's worse. Maybe I should hold this idea for now. Is E exact a thing? Yeah, right, it doesn't help here. So what exactly is going on here? We have a goal that, so if we have some, I'm trying to understand what it is doing here. So if we have some X, which is a type, and we have a goal that is an ensemble over X, and then we try to say downcast full set. Right, cannot infer the implicit parameter. So why is this happening? Because I'm pretty sure if I say exact full set. Oh no, it can't do that either. Neither can E exact. Can I say apply? I can definitely apply add full set, which is basically like without the implicit parameters. Ensembles dot full set. Right. Oh, I'm a stupid. Can I say this? Yes. I've been using this notation here for instead of the actual thing. I can say exact. Why can't I say downcast? Probably because. Okay, this is a very subtle thing. Because it's trying to first convert this into a construction and then pass it down into the LTAC, as opposed to preserving it as a term with holes and then passing it to the exact tactic, which can understand the term with holes. Try uconster. Uconster works. We could also say open term. No, open conster. That also works. I would very much rather use open conster here, and I can do that if I just stick it in here. Can I do that now? I can. If I say no, not yet. Not yet. Let's check this definition here, because check uses a very check expects an open term as well. So right, this definition type checks now. I'm gonna copy this open const around. I could define downcast as an LTAC notation, so that I don't have to specify open conster whenever calling it, but I'm not sure exactly what are the implications of doing that right now. Okay, so where did we get to? Okay, intersection is open. Yes, that's an intersection. The union is also open, and the empty set could probably say empty set like that. Is that gonna be enough? I think so. So, right, we also need hint resolve. Now, same for the full set. Okay, so what we've been doing so far has been fairly technical and related to the internals of Coq. Let's switch that up for a second, and let's define some example topologies. I'm gonna import program for this. I can define records using program really easily. So let's say we want to define a discrete topology on some set X, right? So a discrete topology, in a discrete topology, the set U is open when always. That's the definition of a discrete topology. Any set is open. Now, we've only defined what the open sets are, but to define a topology, we also need to prove these three closure theorems. And what program does for us is that it lets us include the proofs outside of this definition using convenient things that will also get, oh, no obligations remain. That's not fun. Local obligation tactic. Let's make it so that it doesn't get rid of the obligations. So using convenient syntax, we can actually get other like the proofs that we need for a topology. We can provide them in proof mode using tactics. So, right, we would like to prove that the full set belongs to this specification of being open. Well, that is simply true. And in fact, we can probably use auto at this point. No, auto, no, easy. Oh, my favorite, trivial. Oh, that doesn't work. Okay, apparently it's not trivial, but it's easy. Next obligation is that the union, the intersection of two open sets is open, but here any set is open, so by the same reasoning, the intersection must also be open. In the third case, the exact same thing. We don't need to check anything. Now, that is probably the simplest topology that there is. Another really simple topology is the co-discrete topology on X. And this is going to be slightly more complicated. So in the co-discrete topology, exactly two sets are open. So for U to be open, either you have U is the empty set, or you have U is the full set. Only those two sets are open. So we have to show that the full set is open. Actually, I'm gonna add simple to here, so that I don't have to write it out. So we have to show that the full set is open. As we see here, we have to prove that the full set is equal to itself. That's trivial. Not trivial enough. Okay, that is easy. Oh, apparently it's not easy. Okay. We'll have to specify explicitly that in this disjunction we want to go into the right branch and then apply reflexivity. QED. Next obligation. Right, so we have the intersection of two sets that are each either empty or full. That's gonna be fun. So we have some X, we have some U and V, right? So we have the assumption that either U is empty or U is full. And what I'm gonna do is introduce this assumption and destructure it. So here we have the assumption that U is equal to the empty set, and in fact I'm gonna immediately apply this equation to replace U with empty set. And similarly, I'm going to do with in the other branch. And now we have the assumption that this assumption here, and I'm going to do the same thing with it. And now we have 4 cases to consider. In this case, we have a lemma from our set theory library. Intersection empty left, I think. Right. So what we did is we replaced intersection empty something with empty, because that's how it is. And now we can use ATA, because, well, this is trivially true. I can probably also use now. No, I cannot. We have to use ATA because it has to do some branching. I can use ATA here as well. This branch is exactly the same because we still have the empty set on the left. This branch is different because we have the empty set on the right. So if we try to do left here, wouldn't work, because there is nothing that matches the theorem in our goal. Awesome, we're done. And in the final case, we actually have no empty sets. We have to come to this conclusion, which is different from the other 3 cases. Here we apply intersection full left, which says that full intersection something is that something. Now we have full set equals full set. That is true. And then the final obligation is that an arbitrary union of the sets is what I was going to say. An arbitrary union of either empty sets or full sets is either empty or full. And I am actually missing a fact from my library. So if we would, I think I am. Okay. If we have some X, some indexing type, we don't care, some family, and we have a proof that the family is all consisting of either empty sets or open sets, full sets. We need to prove that this union is either empty or full. So here we actually need to use a bit of classical logic. What's the exact bit that we need? So we need to figure out when are we going to go to the left branch and when are we going to go to the right branch. And we go to the left branch exactly when at least one of the sets is empty. We apply classical logic. We use the law of excluded middle to this, applied to the statement that there exists some index such that Fi is the empty set. Right, we need to import classical logic. Good. So, when we destruct, we have 2 cases. In the first case, we get back an I. We can bind that to a name. Okay, so in the first case where there does exist something like that, we go to the left and then we apply, we have a theorem for that. A theorem. I need to search. It's not going to be unique empty set family intersection any empty. That's the theorem that I want to use. Okay. Huh? What's wrong with you? Oh. Oh, no. We're not doing the intersection, we're doing the union. So here we have to check whether any of them is full. And oh, okay, I did implement that. That's the bit that I thought was missing. Right, here we go to the right branch. Apply. Right, so here we would need to show that f of some I is equal to the full set. I here is the existential variable. It's a variable that's been introduced at some point in our proof, as in to be filled in later, and we can fill it in if we apply this equation here. We're gonna like instantiate it with this I, just like that. So what we did here is we used this equation and that instantiated the existential, and the existential was introduced by doing apply, which, so if I try to do apply, I would say unable to find an instance for the variable I. And the reason that pops up is because if we look at the type of the theorem, it has as one of the parameters this I0 thing, well, I, and it doesn't know what value to pick for it. It can't figure out what value to pick for it from the conclusion, from the way we match with the conclusion. And what we're saying is basically don't worry about it, we'll specify a value later. And we can say apply H, that's gonna work as well, where we would not, we could say assumption, no, we can't say assumption. We can say assumption, which is a version of assumption that is able to unify existential variables. I think I'm gonna go with the assumption. That seems very explicit. So, otherwise we have no set is in the family is full. So all sets in the family must be empty. Do we have any interesting way of showing that? I don't think we do. That is not very good. I might need to extend my library with some facts that could be used to show this, but just as a quick thing, we could require import classical ensemble syntactics. Left. So right. What was I trying to say? We can apply set extensionality, we can remove set theoretical notation, basically turning the statement into a bunch of logic regarding like conclusions. We can prove this in logic now. So suppose we have some x, and suppose there exists some I such that x is an fi. Now, how is this possible, right? what is fi exactly? We have an assumption P that tells us what fi is. It's either empty or full. Now let's destruct pi. So we apply p to I, which is going to instantiate this, and then we're going to get a disjunction of two things. Either f is the empty set, or in the other goal we would have that f is a full set. And we would like to immediately replace fi with empty set in all of our things. Apparently it can only do it in the goal. Okay, I'm gonna introduce this as an equation labeled E. We have two cases here. I'm gonna rewrite E in everything. So we replaced fi with empty set here. Now that is not possible. X is in the empty set. We can use unset to verify this. I can use set solve, which is like a very powerful tactic that solves all set tautologies. Now otherwise we know that fi is the full set, but here when we did cases with the classical logic, we like in this branch we are assuming that there is no full set in our family. And that's a contradiction. Let's give this a name. And this contradicts with the statement here. So we can apply n, which is to say that we don't agree with n. And so to show that, we need to show that there does indeed exist some I, and that's the I that we have here, and we have this equation here exactly. And just like that, oh, we're missing something. Oh, we're missing the other direction of the implication. The other direction of the implication is basically that the empty set is a subset of our set that is in fact always true. The empty set is a subset of everything. And just like that, we have defined a co-discrete topology on the set X, which is a slightly more interesting thing than a discrete topology. We could also define the cofinite topology, I suppose. Before we can define something like familiar like the topology and the real numbers, we would have to introduce the concept of a basis, which I think is not going to fit in this stream. But as a final kind of thing, let's define the cofinite topology. So for that, I'm actually going to need another import, lists, because when we talk about that's gonna clash with this in. Okay. When we talk about finite sets in Coq, we usually mean that a value is an element of some list. And in Coq, all lists are finite because they are an inductive data type, and everything in Coq terminates, including lists. So a set in the cofinite topology, a set is open when either it is the full set, or there exists some list of points, a finite list of points, such that U is precisely the set of elements of this list. What did I do wrong here? What is the order of the arguments here? Let's do it like this then. Should probably clean this up at some point. Right, so it takes the argument first. Okay. Okay, let's say it this way. U is the set such that X is in the set whenever X is in L. That's a bit notation heavy. Hopefully we can say it more nicely later. So again, we have 3 theorems to prove here. The full set is an open set because we said so. The intersection of 2 sets. So we have that's going to be a complicated theorem. So we have, for U, we have 2 cases to consider. Either it's the full set, or there exists some list Lx, and the same for V. No, it's not Lx, it's Lu. And then Lv. So we have 4 cases here. The first case, we go left, because we have 2 full sets. Their intersection is the full set. Wait. That is not what the cofinite topology is. We take the complement, because it's a cofinite, so the whatever is missing, whatever is missing from the set has to be a finite set. So we would like U to be exactly the statement that it's not in the list. And then through the empty list, this covers the full set, and what we need to cover is the empty set. Okay. Now, to prove that the full set is in this topology, we say right, and we take the empty list. The empty list, so the set of elements that are not in the empty list is all elements. Let's apply set extensionality here. Actually, do we need that? Yeah, let's do that. Actually, first, before we do that, let's simplify so that it turns from in X empty list, it turns to false, because nothing is in the empty list. Then we can use set solve. I think, yeah, it should handle that. Apparently not. Okay, let's do that manually. Extensionality, remove set notation. Then we have 2 branches, two directions to consider. Actually, can we use intuition here? Yes, we can. Both of these are total. No. Why can't we use intuition here? Why didn't set solve work then? Okay, so both of these are intuitionistic tautologies, so we can use the intuition tactic here. Not a big deal. So we have 2 empty sets. To prove that it's an empty set, we apply intersection empty left. Okay, if here we have the intersection of the empty set with some v, which is again go left, we apply the intersection. Here we have still the empty set. Now we apply intersection on the right. The empty set is on the right, that is, of the intersection. And now this case is the most interesting. Here we have to, we have two lists, and then we have the statement that U and V is actually the complement of these two lists. And we have to prove that the intersection of these two sets is representable as a list. And to do that, we have to consider the intersection of two lists. No. Intersection complements. Yeah, we have to take the union of the two lists because they're complemented. And well, the simplest way to take a union of two lists is to consider their concatenation. So we go to the right branch and then we say exists Lx plus plus Ly. Lu plus plus Lv. And now we have to prove that the intersection of these two sets is exactly the same as this set. Again, set extensionality, and then we remove set theoretical notation. Intuition probably not going to work here. Let's do this very manually. In fact, let's unfold in. Not this in. This in. Okay. So suppose we have some. Suppose we have some x, and it is in neither Lu nor Lv. So we have to prove that it's not in their concatenation. Well, suppose it was. Is there some lemma in this list library? Yes, there is. So if it is in either, we use this lemma and we apply it to the fact that it's an either. So we have a theorem that a lemma, right. So we have a lemma in the list library that says that if something is in the concatenation of two lists, it must be in either of them. So we destruct, we basically ask, okay, which of these is it in? And we get two branches, and in either branch we get a contradiction. Because here we have it's in the first list, but we know that it's not in the first list. That's a contradiction. Similarly, here we get that it's in the second list, but we know that it's not. So we can in fact say that in both branches it's a contradiction. And okay, so let's prove the other side of the inclusion. So we know that it's not in the concatenation. We have to prove that it's neither in the first list nor in the second. Let's focus on the first one for now. Again, let's see what is a lemma that we could use here. We could use in or app. So we have to prove false. To do that, we can apply p. So for that we need to prove that X is in either in the first list or in the second list, and we can do that through this lemma here. So we need to show that it's either in the first or in the second, and we know that it's in the first. That does not conclude the proof. This does though. And actually our proof for the second branch looks exactly the same, but here we go into the right branch of the disjunction. And just like that, oh, we have one more obligation. We need to prove that a union of open sets is open, like a family. And for that, so what we're gonna need to do is take an intersection of all the lists that participated in the family, which is a very non-constructive operation if you think about it. Now, I can't immediately come up with a way to do this proof. And I've been going for like an hour and a half now, so I think this is a good point to wrap up. So I guess we will get back to this theorem in the next stream and probably also define some alternative ways to define a topology. Thanks for watching. See you next time.